Okay, we will go through some important points in the class 12 physics chapter 2 electrostatic potential and capacitance. Okay, when an external force does a work in taking a body from a point to the against a force like a freeing or gravitational force, that work gets stored as potential energy of the body. So when the external force is removed, the body moves, gaining the kinetic energy. That is, it is converting that potential energy into the kinetic energy and losing the equal amount of potential energy. The sum of kinetic and potential energies is thus conserved. That is, when we both add, when potential increases, kinetic decreases. Kinetic energy increases, potential energy decreases. That is conserved. Forces of this kind is called conservative forces. Spring force and gravitational force are the examples of this force. Okay, we bring a test charge Q from point R to the P against the repulsive force. So here this is a positive charge. We are bringing a test charge that is also a positive. So against the repulsive force, then that energy is stored as a potential energy on this charge. Okay, so when you release the charge, then the charge moves, gaining the kinetic energy. That is, that potential energy converted into the kinetic energy. So the stored potential energy is used to provide the kinetic energy for the charge Q in such a way that the sum of the kinetic and potential energy is conserved. Okay, so this is the work done from point V to R. So the here you see work done by the external force. Okay, this work done by the electric field is negative of the work done by the external force. So here see, work done by the electric field is negative of the same work done by the external force. Therefore, we define the electric potential as the difference between the 2 points as the work required to be done by an external force in moving without exerting charge Q from one point to another in the electric of any arbitrary charge configuration. So when we move the charge, that is path independent work done. It means that work done by the electrostatic field in moving a charge from one point to another it depends only on the initial and final points and is independent of the path taken. Okay, this is the fundamental characteristics of the conservative forces. Electrostatic potential energy at infinity they are taking as 0. Okay, work done. So work done by the external force equal and opposite to the electric force. Electrostatic potential. The force is QE where E is the electric field. So here when you take the difference, we have final point minus initial point we are taking. That is potential at the final point minus initial point. Work done by the electrofield bringing a unit positive charge from infinity to a point is that is the potential at that point. So what we have to learn from this figure is the work done is independent of the path. Work done is only depends only initial and final point. So you can go by this path are straight. So work done is depend only on the initial and final points. Okay. Potential due to a point charge. Okay, the point charge potential due to point charge depends on the distance. So here potential due to point charge it decreases as our distance increases. So voltage will decrease as we increase the distance, that is the R. This is the voltage and potential and electric field curve versus the distance. How the potential varies with the distance, how the electric field varies with the distance. So here this is the formula: potential at point P, the distance r, and for the due to the charge. So the units of this work done: joules, charge, coulomb, potential, voltage. So now we find a electric potential due to electric pole, dipole. So dipole will have two charges, plus q and minus q, with a separated distance 2a. Okay, the total charge is 0. Plus q minus q will cancel. So this is the dipole, and the direction of the dipole moment is from minus q to plus q here, and this is the angle for from this point, from the center of the dipole to the point where we measure the potential, and this is the distance, this is the angle. So the potential at this point depends on the distance, angle, and the dipole moment. See how the potential falls off at large distance due to single charge and the dipole they are given. So you can also measure the potential at this point separately due to this charge using superposition principle. Okay. So this is the potential at distance r with this angle, with this dipole moment. So cos 01, cos 181, then the potential formula will become like this. Okay. So this they are comparing with a single charge versus a dipole. How the potential due to dipole varies, how the electric dipole potential falls off with the distance. Okay. Potential due to this system of charges. For a uniformly charged spherical shell where q is the total charge of the cell or the radius, the electric field inside the spherical conductor is 0. This implies that the potential is constant inside the cell, and no work is done in moving a charge inside the cell because potential is constant. The potential difference is 0, so there is no work done in moving a charge from one point to another within the cell. That is important. So here potential due to this charge cancels due to this charge at some point. Okay, so here you see, give the sign of potential energy difference of a small negative charge. When you have a negative charge between P and Q, the potential energy at Q, because the negative charge will be attracted towards the positive charge. So here potential energy at Q will be more than the potential energy at P, but kinetic energy at P will be more than the kinetic energy at Q. So this is a negative charge, here it will repel. So here potential energy at A will be greater than the potential energy at B. Okay, here for the negative charge. Work done is a charge in the potential difference. Work done will be positive and moved over the uncomfortable direction, repulsive direction. UQ potential surfaces on a surface the constant value of the potential, everywhere voltage will be same. UQ potential surfaces of this single point charge is a constant here. See here, this is a single charge. These circles are the UQ potential surfaces because potential varies with the distance r. So same distance will have the same potential. This is how the electric field lines. Electric field lines. There is no potential development in any 2 points on the surface, and no work required to eliminate test charge on the surface. The electric field must therefore be normal to the equipotential surface. For a uniform electric field, if you have a uniform electric field in the x-axis, the equipotential surfaces are the planes normal to x, that is YZ plane. Okay. Electric field and potential. Electric field, difference of the differentiation of the potential dV by dt. Electric field is in the direction in which potential decreases. Okay, let's see first. The magnet is given by the change in magnet of the potential displacement normal to the equipotential surface. Potential of the system of charges. Work done is charge into potential for the system of charges. This is the formula. Here when we bring this charge, here the work done will be 0 because this electric field due to this minus q and plus q will get cancelled here because we are bringing this at the center. The electrostatic potential at E is, that is center, is 0. Okay, A and C and B and D will cancel out. Here d root t is the diagonal distance between the A and C. When you bring a charge at C, when a charge at A is already there, then the diagonal distance is the dt. So square root of d square plus d square 2 root t, that is d root 2 is the diagonal distance. Here you see d root 2 is the diagonal distance. The work done depends only on the arrangement of charges and not how they are assembled. Okay, you can reverse this order and check. Okay. Okay, the easy work done for charge into potential. Potential energy of a system of two charges in an electric field. Okay, here this unit conversion I have mentioned. So they are converting into meters. Potential energy difference, they are final minus initial. Electrostatics of conductor. Inside the conductor, electrostatic field is 0. Okay, and there is no current inside or on the surface of the conductor. Electric field is 0 everywhere else. In the static condition, the free charges are so distributed. Okay, electrostatic field inside the conductor is 0. At the surface of the charge conductor, electrostatic must be normal to the surface at any point. Interior of the conductor, and I have no excess charge in the static condition. There is no net charge at any point inside the conductor. constant through the volume of the conductor, and this electrostatic potential is constant through the volume of the conductor. Potential difference any 2 point inside or in surface of the conductor. At the surface of the conductor. Shielding, electrostatic shielding. Consider a conductor with a cavity with no charge inside the cavity. A remarkable result is the electric field inside the cavity is zero. When the cavity has no charge, then electric field is zero. Like this. All charges reside only on the outer surface of the conductor with the cavity. The field inside the cavity is always zero. This is electrostatic shielding. See here, they are bird on the electric power line. Nothing happens to the bird. A man standing on the ground touches the same wire and gets the fatal shock. Why? Because potential difference is zero and the bird is sitting on the wire. Current passes only there is a potential difference. Bird doesn't have the potential difference because it is sitting on the same line. Dielectric and polarization. Dielectrics are the non-conducting substances in contrast to the conductor. They have no or negligible number of charge carriers. Polar molecule and non-polar molecule. Polar is water and HCl, non-polar hydrogen, carbon dioxide. Where polar and dielectric develops a net dipole moment in the presence of the external dielectric, it develops a net dipole moment. Positive end of the dipole remain unneutralized. The negative ends of the you can go through this. Capacitor and capacitor. A capacitor is a system of two conductors separated by an insulator. You have two conductors separated by an insulator. Conductor 1, conductor 2. Potential difference is the work done per unit positive charge in taking per unit positive charge in taking a small test charge from the conductor 2 to 1 against the field. C equal to Q by V, charge by potential. Micro 10 power minus 6, 10 power minus and nano 10 power minus 12 pico. Parallel plate capacitors. So in the vacuum, this is the capacitance. Area cross section divided by the distance. This is permittivity of the free space. When you insert a dielectric material, then capacitance changes. With the dielectric constant K. Introduction of the dielectric constant K is the permittivity of the medium. So this is permittivity of the vacuum. Effect of dielectric. The potential difference decreases by a factor of this while free charge on the plates remains unchanged. The capacitance thus increases. So effect of dielectric, capacitance increases. The charge remains same. And we connect two capacitors in series. So here we are connecting a negative to positive charge. This is how you will connect capacitors in series. The resultant total capacitance when you connect two capacitors in series, 1 by C equal to 1 by C1 plus 1 by C2. Okay, when a capacitor in parallel, we connect the same charge, see here negative to negative, positive to positive. Okay, the resultant capacitance is addition of the resultant capacitor is C1 plus C2. See in series 1 by C equal to 1 by C1 plus 1 by C2. In parallel C equal to C1 plus C2. Parallel we connect the positive negative to negative. Energy stored on the capacitor, that is half CV square equal to half Q equal to CV, so half QV. The electrostatic force is conservative, the work required to store in the potential energy of the system. This work is stored the potential energy of the system. Is going that no charge is lost. The final energy is one of the energy, whereas the remaining energy is gone. There is a transient period before the system settles. In this situation, during this period, a transient current flows from the okay. So you can go through this example. How energy is lost. Okay. This is summary actually, which we have already seen.